Liquid fuel properties are important to understand how it can be ignited, how the flame will spread over this, and how fast it will burn. So, we will define three temperatures for this basically first. One is called flash point. Okay, now what you do is you take a crucible, a brass crucible, and try to heat. So, I have a crucible in which liquid is kept. This can be closed or open. So, there are techniques to do this: closed flash point apparatus or open flash point apparatus, etc. But some small difference will come in the flash point. So, I try to heat this slowly and stir this also, so that the liquid at the uniform temperature. So, now I also know the temperature T. Okay. So, now what happens? When the temperature increases slowly and reaches the temperature called flash point, some vapors are produced over the surface. Okay. So, it is not, please understand that evaporation process is a surface phenomena. So, what happens is when the surface is at a particular temperature, need not be at the boiling point. So, for example, I have water in a beaker. Just close this with the lid. Okay. What happens? You will see when you open the lid, you will see that water particles are formed at the bottom of the lid. Why? This is because the evaporation has taken place, and the vapor which has come out is not going to go out because lid is there to cover it, but it condenses over the lid. So, you see the water particles on the lid. So, similar to that, you need not reach the boiling temperature. At a given temperature, there will be some amount of vapor which is formed. It's called the saturation pressure for the vapor, which is actually imparting the pressure over the liquid surface. So, for any temperature, there is a relationship between a given temperature and the vapor pressure, correct? So, there is a temperature called flash point at which enough vapor is produced and it has mixed with the air from the atmosphere, and if you put the ignition source like a candle flame or a spark, it will produce a flash. Flash means instantaneous flame will be produced over the surface. Then when you, that's all, then this flame, because vapor is consumed, then no flame will be formed. So, you have to wait for some more time to form the vapors and again ignite it so that it flashes. So, flash point is the temperature at which enough vapor is released from the liquid fuel surface to form a mixture with atmospheric air that is ignitable. That is, when you put a external ignition source, a instantaneous flame is formed and consumes this reactant mixture of vapor and atmospheric air. Now, continue to heat it. So, now you know the temperature. There is a minimum temperature at which this occurs. Okay, lesser than this temperature, nothing will occur. You cannot ignite it at all. So, you have to reach a particular temperature called flash point to see a flash or instantaneous flame upon ignition. Okay, now, so that means that there is a ignition source which is required to cause this. Now, coming to slightly higher temperature than this. So, now continue to heat this, stirring it so that uniform temperature reaches. Now, I reach a temperature called fire point. So, now what I do? I ignite it. Now, you will see that at the, so this is flash point. The fire point, there will be a flame which is going to establish over the surface. There will be a flame. You remove the external heating or the ignition source, nothing will happen, the fire will continue. This is called fire point. That means I can ignite the fuel and make it sustainable on its own. That is, I don't need the ignition source to ignite the mixture anymore, because now what happens? The fire is established over the surface of the pool. This is liquid pool, and the heat coming from the flame will be enough to generate the vapors from the surface and feed the flame. Please understand, this fire point also is less than the boiling point. Okay. So, flash point is the minimum temperature at which a ignitable mixture is formed. Fire point is higher than the flash point, where a sustained flame is generated over the pool surface. Then coming to boiling point, which is the highest temperature, where volumetric phase change. That is, for example, these are surface phenomena. Entire volume is at boiling point. That means you will see that the temperature further will not change until the liquid is converted into vapor. So, boiling point is called saturation temperature, where phase change occurs without causing any change in the temperature until the entire liquid converts into vapor. This is actually pressure dependent. So, for example, for water at 1 atmospheric pressure, the boiling point is around 100 degrees centigrade, 99.6 degrees centigrade. But if you increase or decrease the pressure, this value will change. Okay. So, if you increase the pressure, the value will increase. If you decrease the pressure, the value will decrease. The boiling point will decrease. At 1 atmospheric pressure, the boiling point is called normal boiling point. Okay. So, when a liquid pool burns, slowly what happens is the heat feedback will heat the liquid pool itself. But once it reaches close to the boiling point, further change in the liquid temperature will not occur. So, what happens is the heat feedback will only supply for latent heat of vaporization, causing the liquid to change its phase to vapor. That's it. The liquid temperature will not change much. So, that temperature is called equilibrium temperature, at which the sustained vaporization occurs at a steady state. So, now other properties. So, these are the three temperatures for liquid fuel: flash point, fire point, boiling point. Now, another important property is latent heat of vaporization. So, what is the amount of heat which I have to supply to a liquid in order to change its phase from liquid to vapor when it is at the saturation temperature at the particular pressure? Do you understand? So, basically you may wonder, saturation temperature, boiling point, it should be at boiling point? No, not necessarily. See, please understand that when there is a liquid surface and vapor over the surface, there is a vapor pressure which the vapor applies over the liquid surface. So, at that pressure, the corresponding saturation temperature is enough. Do you understand? That means I don't need to go to boiling point at all. So, latent heat of vaporization is the amount of heat which I have to supply to convert the liquid to the vapor at the particular pressure. Do you understand? So, heat required per kg of liquid is actually kilojoule per kg. Per kg of liquid to cause phase change from liquid to vapor. That's the latent heat of vaporization. Again, it's a function of temperature and pressure. Now, these are the properties, basically what we can say as thermal properties. Now, coming to one of the physical properties of liquid fuel, surface tension. Basically, surface tension is the energy required to increase the surface area of a liquid surface in contact with the gas phase or any other phase basically, but predominantly gas phase is involved because we are talking about the interface between the liquid and the gas. So, when there is a fluid, molecules will be there in the fluid, there will be intermolecular forces. Basically, for liquids or condensed, like if you give a condensed fuel, so density is very high. So, the intermolecular forces will be predominant for the liquid. So, when you want to have some surface interaction with the vapor phase, liquid surface and vapor phase interaction, then the liquid has to overcome the intermolecular forces. See, a simple test is put a beaker in a beaker of liquid, put a capillary tube. How the liquid rises in the capillary tube depends upon the surface tension, one important properties. Okay. So, the cohesive forces of the intermolecular forces, what we call, that should be overcome by the surface tension so that the liquid rises. So, that is a surface phenomena basically. Why it is important for us? Normally, for liquids, it is important only when you try to atomize the liquid and put as a spray. So, for example, in our case, not for fuel it is useful, it is useful for producing mist or sprinkler which sprinkles the water as droplets. For that, surface tension is important. How the droplets are formed, what is the force required to cause the breakup of the liquid and cause formation of the droplets, etc., depends on one of the important property called surface tension. This is one aspect. Second aspect is, if you take a pool of liquid, when it burns, a flame is established over the pool. We have seen that after the fire point is reached, the flame is established over the pool. Now, what happens is, you can see the pool fire, which is actually going to surround the circumference and anchor over there, and the distance between the flame and the surface will increase as you go from the rim or the edge to the center. So that means there is a non-uniform heating of the liquid surface. So the liquid surface, when it is non-uniformly heated, the temperature gradient will cause what is called a surface tension gradient. That is, surface tension also will be different at the edge and at the center. So the surface tension gradient will trigger a flow of the surface from low surface tension point to the high surface tension point. That is from the high temperature to the low temperature. So this trigger of this motion at the surface will cause the internal circulation in the liquid itself based upon the viscosity of the liquid, etc. So this convection, which is triggered due to surface tension gradient, is called Marangoni convection. This actually increases the burning rate. So in the context of burning, surface tension aids in Marangoni convection for liquid pool burning. So that is one of the property. In case of formation of droplets also, surface tension is very important. Okay, now these are the properties. Now all these properties basically vary as a function of temperature and in some cases with pressure. Okay, so there should be proper tests and analysis which will give you correlations, etc., to understand how the variation of these properties occurs with temperature and use that to analyze the particular situation. This is for one particular component. So, for example, for CO2, there is a variation of these properties with temperature. Okay, like for example, K, Cp, rho, etc. will vary. Now, for a mixture of gases in the products, for example, there should be a mixing rule. Then only you will get a Cp of the mixture, thermal conductivity of the mixture, density of the mixture, etc. Okay, so you first need variation of these properties as a function of temperature and pressure, further mixing rules to get the mixture properties itself. Now coming to the solid fuel properties. Solid fuel is, previously I have told that it is classified as a charring fuel which produces char, that is carbon and ash, and other cases like plastics, etc., is called non-charring, because the plastic, etc., when it burn, it will not leave a char. Okay, so simple definition for charring fuel is which produces a carbon material upon burning, and this carbon material can also contain some minerals called ash. So together this is called char. Other solid materials which doesn't produce this carbonaceous material, it may be some impurities can be produced. For example, if a plastic sheet is burnt, some impurities can come out but not char. So it will just burn. So that is non-charring. The other classification is non-charring. So solid materials like wood, coal, any biomass, vegetation, etc., are charring type. Okay. Other than this, let us take say plastics, polymers, etc., they are non-charring. So the non-charring type of fuel will have different burning behavior when compared to the charring. So let us see one by one first. Let us take charring material. Previously I told that it has 4 components. So I do what is called a proximate analysis to bring out the percentages of these 4 components. What are the components? Moisture, trapped water, then volatiles, trapped gases. These trapped gases can be CO2, CO, H2, CH4, C2H2, etc. Several gases can be there. So what basically happens is these gases are trapped in the solid material, cannot come out until they are heated to a particular temperature. That is, the solid is heated to a particular temperature. Then obviously some fixed carbon will be there and ash. These are the 4 components which you find using proximate analysis. Proximate analysis. So moisture, volatiles, fixed carbon and ash. So now what you do, you try to take a solid sample and try to heat it. So this apparatus is called thermogravimetric analyzer. For example, thermogravimetric analyzer. So I put the solid sample in this. I can use any agent, nitrogen or oxygen or air. But what I have to do is I have to send hot gases through this, and there is a specific heating rate which I can set, like say 30 degree per minute, 40 degree per minute, etc. If you set that, then the solid sample will be slowly heated, and when the solid sample temperature is going to reach a temperature of say 100 degrees centigrade, that is 373 Kelvin, the water trap will be evaporating and it will come out as a water vapor. Then there will be some reduction in the weight because of the leaving of the moisture from the solid. Then nothing will happen, the mass will not change. Now you try to further heat it slowly or whatever is the heating rate, then you reach a temperature in between 500 Kelvin and 600 Kelvin. What happens? The gases which is trapped inside, okay? Please understand that volatiles are the gases which are non-condensable. So they are trapped inside as gases itself. They try to come out. Okay. So what are these gases? CO, CO2, CH4, C2H2, C2H4, hydrogen, etc., nitrogen, even some oxygen. Everything will be trapped inside, and these gases will come out when the solid is heated to around 500 to 600 Kelvin. Next, that's all. Then some mass will be lost, and this mass loss basically will stop once all the volatiles from the sample has come out. Now what is remaining is the char, which is the combination of fixed carbon and the ash. Ash is mineral, silica, etc. So now the char, when you use a nitrogen environment, nothing will happen. The char will remain as char only because it will not react. But if you use oxygen based environment like air, etc., and when the char is heated to a temperature of about say 900 to 1000 Kelvin, then oxygen from the ambient will diffuse to the hot char surface and surface reaction occur, say C plus O2 giving CO2. C is solid, okay. Now I can also have some reactions, C solid plus I can also send CO2 giving 2CO. Please understand that this is C plus O2 reaction is the oxidation reaction. C plus CO2 giving CO is a reduction reaction. But both can occur. But the carbon should be hot enough. That is the main important thing. Then this can occur. Similarly, H2O also can react. C solid plus H2O giving CO plus H2. So that means based upon the agents, but nitrogen will not react at all with solid carbon. So if you have agents like O2, CO2 or steam, then you will see that the carbon can be converted into gaseous products. Solid carbon can be converted into gaseous products. So that will show the mass loss rate of that also. So in finally what happened, based upon the ash, whatever be the percentage of ash, that will remain. So the proximate analysis gives you this information of how much moisture is there, how much volatile is there, fixed carbon is there and ash is there. Based upon that, you will know how much heat has to be supplied to release the volatiles, how much temperature heat has to be supplied to increase temperature to char oxidation temperature, etc. Because the percentage of this will vary, with the solid fuels. Okay, now solids those do not leave behind char are called non-charring fuels. Okay, now non-charring fuels, let us take examples like say plastics, wax is a non-charring fuel, then PMMA. Okay, see for example, if there is a monomer of a particular, say monomer is a liquid fuel, when you polymerize that to get a polymer, then what happens is it will get a solid. Okay, so it is like wax type solid only basically. So what happens is when you heat this solid, non-charring solid, there are two things which can happen. It may melt, liquid is formed, then it will burn as a liquid fuel. It will be vaporizing to leave the vapors, then vapors will mix with the oxygen in the atmosphere and form flame. That is one way. Or in some cases, directly you can sublimate. That is, sublimation is the process of converting the solid directly to gas. When you do that, you have to give the latent heat of sublimation. So when you do that, directly after reaching a particular temperature, solid to gas will form. So monomers first are created when the polymers melt. That is one route. Monomer reaction with air, that is one route. For example, PMMA will now convert to its monomer and burn, or PMMA can directly produce vapors of monomer. There are situations like that. Okay, now when you take the non-charring or charring, for example, a process called pyrolysis occurs first to release the gaseous components or volatiles. So pyrolysis is the process of extracting the gaseous components from the solid fuels. It may be charring or non-charring. So how much temperature the solid fuel should reach and how much heat I have to supply to the solid fuel in order to extract the gaseous fuel from them. That process is called pyrolysis process. Okay. Now previously we told that major heat release in the fire is caused from the gas phase reactions. Okay. Now once the volatiles are released, so please see this, for charring and non-charring, first of all heat should be supplied to a particular extent so that a pyrolysis temperature is reached, at which pyrolysis can occur by taking more heat. Then you will get the heat release happening in the gas phase because of the burning of these volatiles or the pyrolysis gases with the atmospheric air. Okay, now part of this heat should be supplied to the solid surface itself in order to keep on extracting the volatiles. If the heat feedback is not there, then the volatiles will not come out, then the burning will stop. So heat supplied to the solid fuel to extract gaseous component is called heat of pyrolysis or heat of gasification. Like heat of evaporation, latent heat of vaporization, heat of pyrolysis is important for the solid fuel. Okay, now when there is a sublimation process, I supply heat of sublimation, latent heat of sublimation. Okay, so these are the important properties of the solid fuel. Okay, again experimentally determined. So now the routes are melting and vaporization. Then that means you have to supply heat of melting for those fuels. Direct sublimation, supply heat of sublimation. In both the cases, for releasing the gases, I have to supply the heat of pyrolysis. Okay, so these are important properties, okay, of the solid fuels. When you want to use any solid material for construction or any domestic usage, first of all you have to qualify them for these properties and see whether for the environment where it is used, this will not cause any fire hazard. Okay. So now coming to the next point, definitions. Now I will go to definitions related to fire. So definitions related to fire, let us see. First, we will see some definition related to ignition of a material. See, fire is caused by ignition. So let us first see some important definitions or terminologies with respect to ignition. First one is, so why we are doing this? Because fire is initiated by ignition of a material. So everything cannot be ignited very easily. For example, ignition of wood is much complex than ignition of a liquid fuel. Within the liquid fuel, if we take say petrol in a bowl and diesel in a bowl, ignition of petrol is much easier than ignition of diesel. Petrol is highly volatile. So ignition phenomena, to understand, several properties are involved in that, to understand that. Okay, now first one is what is called ignition temperature. Mostly this is the temperature at which the ignition can occur. We have seen for liquid fuels flash point. So flash point is the temperature, which is the minimum temperature of the liquid which can produce some enough vapors which can produce a momentary flame or instantaneous flame. So that we can keep. Or if you want to cause a fire, we can go to fire point. So ignition temperature is clearly mentioned for the liquid fuels, like the temperature at which you can cause ignition. Correct. For solid fuels, it is somewhat different. It is not the pyrolysis temperature. Pyrolysis temperature is one in which the gases are released. But what is the ignition temperature? It may be around the pyrolysis temperature, slightly more than that. So that means for different types of materials, the temperature at which you can see a flame over that, initiated over the particular region of the material, that temperature is defined as the ignition temperature. Okay, so that is one of the more important to this. So now, to heat the material to the ignition temperature, what I need is a heat flux. So nothing, if the room is cool enough, nothing will happen. Even though some flammable items are present in the room, unless you heat it to ignition temperature, the flammable material will not be able to catch fire. So there is a heat flux which is called critical heat flux, which is required to increase the temperature of the material from the room temperature to the ignition temperature. So another important definition or parameter is critical heat flux. Ignition temperature, critical heat flux. Now, okay, you have a critical heat flux. This is a property. Yes, the critical heat flux and ignition temperature are properties which are dependent on few more properties, which is defined as thermal inertia. We have already seen that product of density, thermal conductivity and C, rho Kc. This product is called thermal inertia. Then heat of gasification or heat of pyrolysis. So how much heat we have to supply to cause the volatiles to release? Then the ignition temperature. So this will dictate the time taken for the material to be ignited. Okay, so that means a component like plastic can be ignited faster than wood. How it is? Because of the properties associated with the plastic and the wood. Thermal inertia, heat of gasification, ignition temperature, and of course the product yield. Product yield is what? The volatiles. How fast the volatiles, how much volatiles come out, etc. That will also, because when the product come out, then only see the ignition will, we are focusing our attention only on the gas phase ignition first, because once the gas phase flame is formed, then the solid will be further heated, char is formed, then char surface reaction will take place. That is the secondary process. The surface reaction will be secondary process. The primary ignition is basically due to the gas phase reaction. So that means we are looking on how the gases are released from the condensed phase. Okay. So now please understand that thermal inertia, heat of gasification, ignition temperature and product yield, these together contribute to what is called thermal response parameter, TRP, thermal response parameter. So there are standard test procedures to determine it. We will come to that later. Okay. Now, ignition depends on the property of the material, time of ignition, ignition delay, whatever you call. Now, ignition can be classified as piloted or auto. Pilot ignition, as the name suggests, that's the external ignition source which will cause. So when you want to initiate a fire, mostly it is caused by an external source. For example, there's a dustbin of paper waste, etc. Somebody throws a match or a lighted cigarette, etc. on that, it causes the ignition. So external source causes the ignition. Such an ignition is called piloted ignition. Now, fire is there, initiated in a corner of a room, in a dustbin, but that fire now can cause ignition on a second commodity, etc. Okay, because it may heat up the material adjacent to that, some vapors can come out or fuel can come out, that will form a flammable mixture, and this heat, when the flammable mixture itself reaches a temperature called auto ignition temperature, then no external source is required, it will automatically catch fire. So, the piloted ignition is caused by external source, and there are two important criteria for that. One is called minimum or critical volume of the reactants to be present. As I told you, when you heat the liquid fuel to flash point, then only enough vapor will be produced to cause ignition, or else it will not be able to produce the flammable mixture at all. Second one is the ignition source should have minimum ignition energy. If the energy of ignition is not sufficient, then it will not cause ignition. Okay, so these are the two important things. When the auto ignition occurs, there should be a flammable mixture, and it has to be at a temperature which is more than or at least equal to what is called auto ignition temperature. Then, without the aid of external ignition source, this will be ignited. Okay, so these are the important definitions. So, let us see this. Fire is initiated by ignition. For ignition to occur, a minimum temperature called ignition temperature should be reached, and to attain this temperature, there should be a critical heat flux, and the ignition delay is characterized by several properties, including thermal inertia, heat of gasification, then ignition temperature, and the product pyrolysis yield. Together, this is called thermal response parameter. And ignition is classified as piloted ignition or auto ignition. Piloted ignition basically requires an external source with minimum amount of material or mixture, gaseous mixture, which is available, plus it should have a minimum ignition energy. For auto ignition, a flammable mixture should exist at a temperature which is more than the auto ignition temperature. Okay. So now I will stop here. We will continue in the next class.